we're going to go ahead and take a look at graphing a improper rational function, and we're going to limit our graphing in our class to improper rational functions where the degree of the top is exactly one more than the bottom. That's what makes it improper, that this is x squared and this is x. I mean, you could have other things like x to the fifth and x to the third. That would be improper, or x to the seventh and x to the second. Anytime the degree on the top is bigger than the bottom, then we have a improper rational function. But we'll limit it just to one more. And then that will limit the kind of what we're going to call oblique asymptotes we get on the graph to a linear kind of oblique asymptote. Okay, so and if you're interested in an asymptote discussion, that is on a earlier video. You could take a look at finding the asymptotes of a improper rational function. So what we're going to do here is we're going to first find the y-intercept, and that's by putting 0 in. And we got 0 here, here, and here would just give me negative 3 over 1. And there's my y-intercept. And so let me put that here on the graph. And that would be right here at negative 3, right here. Okay, so now let's go ahead and take a look at some of the other features of the graph. By the way, you know, I don't know if I've mentioned about holes in the graph. There aren't any whenever you have no factors canceling with the top and bottom. And I did factor this already for us, but if you factor the numerator, it is a trinomial whose lead coefficient is 1. And what two numbers multiply to negative 3 and add to 2, it turns out to be positive 3 and negative 1. The bottom did not need to be factored, but if it was possible to factor it, I would. Okay, then we use this factored form to find, first of all, let's look at the domain and the vertical asymptotes. And we know, if you've been doing problems up to this point, that the domain and the vertical asymptotes come from the factors of the denominator. It turns out that we cannot divide by 0, right? Any fraction cannot be divided by 0. And so we set this denominator equal to 0 to find the values of x that are not allowed, because if we did allow a negative 1 here, we'd be dividing by 0. So our function, its domain, is limited to the set of all x such that x can be anything but not negative 1. But likewise, if we approach negative 1, we're going to, I mean, not exactly negative 1, but as we get close to it, these values in the bottom will become so small that we would be dividing by a small number and therefore producing a big output of the overall function. And you can see I used the table feature and in my calculator, and it turned out that I ended up with a huge number by going close to negative 1 from the left-hand side. Let's take a look at where I'm at here. Right, if I draw my vertical asymptote here of x equals negative 1, okay, and if I approached it from the left, like negative 1.01, I get something almost pretty much 400. I'm just way down here. So I know on the left side the behavior of my function is going to be way down. Oh, I'm sorry. No, it's a positive 400. It's going to be way up here. Okay. So yeah, it's a positive 400. Then if I approach it from the right-hand side, negative 0.99, I get a really big negative number, and so it's on the right-hand side that its function is going to go way down, right, like this. Okay, so we have behavior near the vertical asymptote, and that is, again, coming from approaching the factors of the bottom, you know, getting close to those values, but not exactly equal to what it would take to get to 0, right? Okay, so now, let's go ahead and take a look at finding the x-intercept and then also finding the oblique asymptote. And so that is over here. We're going to go ahead and look at setting y to 0 or f of x to 0. And if I let y be 0 here, I would get 0 is equal to, and here's my factored form of my original function. And when I cross multiply, it turns out, as I've said before on earlier videos, that the factors of the numerator really are where you find your zeros, because as you do this cross multiplication, the denominator goes away when you multiply it by 0. So it's the factors of the numerator produce the zeros of the function. And it turns out if you use the zero product property here and set x plus 3 to 0 and x minus 1 to 0, you get negative 3 and 1 are the two zeros of this function. So let me put negative 3 here, and let me put 1 right here. Okay, so our graph is taking a little bit of shape here, but we got a ways to go. And the next thing we do is to take a look at the oblique asymptote. In other words, where we believe we're going to be approaching. It's going to be some kind of a linear equation, the asymptote itself. We do that in the divided form of the function. So I'm going to go ahead and take the original function, there it is right here, and I'm literally going to divide x plus 1 into the numerator. And by the way, what I'm doing is getting still an exact value of the function. When I divided x plus 1 in here, I got x plus 1 minus 4 over x plus 1. And I think I go through the division a little more detail on the asymptote video that I did earlier. I used the same function on it. But watch what happens here. This is really equal to the original function, and I just wrote this down here to show you that the original function is equal to this. It's just that this is in what is kind of like mixed number form. It's kind of like taking 7/3 an improper fraction and calling it 2 1/3. It's still equal to it, right? But the advantage here is if values of x got really big in the positive or negative direction, this little fraction would go away pretty much. See 4 over 101 or 4 over 4001, whatever value you put in for x that was big, it gets really small, and the function starts to act like the equation y equals x plus 1. So we're going to say that y equals x plus 1 is going to be our oblique asymptote that we will be approaching for big positive and negative values of x. So let me draw that in here, and that's nothing more than with an imaginary dotted line graphing y is equal to x plus 1. So the way we graph any linear equation is we go up to the y-intercept, and then we start counting up 1 and over 1 and up 1 and over 1, and we get our slope, right, which is 1 to 1 in this because the value in front of x was just a 1. And we're just going to go ahead and plot this line like this. And that is going to be the the oblique asymptote that we're going to approach. Okay, now, let's see what it looks like when we do approach it. Are we going to be, number one, a little bit below or a little bit above, going out for big values of x? And also, do we ever cross this line? And we're going to figure both of those things out over here. So we use our table feature. I don't think I have that function in here. Let me just go ahead and put that in here. And I'll just clear this, and I'm going to use the fraction feature. I already had a function in there that was a fraction. I'm just going to go ahead and change it to this function right here. And you don't have to have it in factored form in the calculator. The calculator will take care of everything that we need. And x squared plus 2x minus 3 over x plus 1. Okay, and now what I could do is I could go to second table, and I could put in these big values. And let's see what happens here. So when I put 100 in, I get, and you can see I was in there earlier, these are some leftover values from another time. But when I put 100 in, I got 100.96. And so what I believe is happening is for big values of x, I am behaving like y is equal to x plus 1, because think about it, when you put 100 into this function, you'll get 101. Well, I got almost like 101. I got 100.96, which means I'm just a little less than 101. And so I think what's happening is I am approaching this underneath. I'm not quite at 101. And I think my function is hugging my y is equal to x plus 1 oblique asymptote from underneath it, right? It's a little less. Let's see what happens when I go ahead and put negative 100 in there. Well, then I get something a little less. It's like I had negative 100 plus 1 is negative 99, but I have negative 98.96, which is a little less than negative 99 from a negative standpoint. So I think actually, if this is a little less negative, right, I'm actually a little above my line, because if I was exactly on this oblique asymptote, it would be negative 100 plus 1 is negative 99, but I'm a little above that, right? I have a smaller negative is actually a little more positive here. So I think what's happening is my function's coming down, and I'm going through this x-intercept that I found earlier, and I'm going to come down like this. Now the question is, though, did I ever cross anywhere? Did I ever cross this oblique asymptote anywhere? Right? Well, let's take a look. And by the way, I'm anticipating this as well. Right here, I could finish this off, because remember, we said as we approach this vertical asymptote from the right-hand side, we said earlier we were going down this way. And so I think I'm getting something like this, right? But just to be sure, is it possible that I cross this oblique asymptote? And oblique and horizontal asymptotes it is possible on any given rational function to cross them. At least it's mathematically okay to have that happen. So let's just see if that happens on this particular function. So what we're going to do is say that if my oblique asymptote is y is equal to x plus 1, I'm going to go ahead and see if there's any solutions to that asymptote function that is also a solution to my actual function itself. And so I'll set them equal to each other and see if there's a value of x that satisfies both. So I cross multiply here, and I get x squared plus 2x minus 3. And then I actually have to do a binomial times binomial multiplication here, and I get x squared plus 2x plus 1. The x squareds could cancel on both sides. And then the 2x's actually can also cancel. I subtracted them, but I could have just as well canceled them. And by the time I'm done, I have a inconsistent statement of negative 3 equals 1, and it does not. And there is no place then that this oblique asymptote is ever crossed. There's no place that this oblique... And by the way, that point, I shouldn't have really darkened in so much. I only used it as my y-intercept to graphing my oblique asymptote, but it is not a point on the actual function. My function's graph is like this and like this, right?